Picture a library with branching signs. A sign that says go left or go right is useful only if the hallway stays short. A binary search tree has the same promise: order gives direction, but balance keeps the walk from becoming one long corridor. In this video, we will build that mental picture in 4 steps. First, the left-right search rule. Second, the height receipt that tells us how many comparisons we pay. Third, how bad insertion order turns a tree into a hallway. Fourth, how rotations repair the shape without losing sorted order. Binary search in an array is fast because the data is sorted and the middle comparison cuts the search space. A search tree keeps a similar directional idea, but in linked branching form instead of one flat array. The binary search tree rule is simple. Values smaller than a node go left. Values larger than a node go right. If the rule is true everywhere, each comparison tells us which entire side we can ignore. To find 40, start at the root. If 40 is smaller, go left. If it is larger, go right. Each step is a decision that removes a whole branch from consideration. The path is the work. The number of comparisons depends on height, how many links the longest root to leaf path has. A short tree gives short searches. A tall tree gives long searches. Same values, different shape, different cost. Balance does not mean perfectly symmetric. Think of a city map with many short branching roads, not a perfect drawing. The tree is allowed to lean a little, it just refuses to let searches drift into long corridors. If values arrive in sorted order and we do nothing, a plain search tree can become a crooked hallway. Every new value goes to the same side. The order rule is still correct, but the search path now behaves almost like a linked list. This is the key mental split. The keys can be in the same sorted relationship while the shape changes the bill. Order tells us which direction to walk. Balance controls how many doors we pass before we arrive. Insertion follows the search path until it finds an empty child position. That adds the new value legally. But legal is not the same as healthy. The new node may make one side too tall. A rotation is local surgery. Imagine a small crane lifting one joint of the tree while the sorted cables stay attached. Only a few nodes move. The goal is not a new order, the goal is a shorter, healthier shape. Rotation is safe because it respects ranges. The sorted ribbon through the tree still reads in the same order. Values below a boundary stay below it, values between two keys stay between them, and the picture moves without forgetting what the keys mean. A left rotation repairs a right-heavy local shape. The right child rises, the old root moves left, and the transferred middle subtree keeps the order rule intact. It is a shape fix, not a value shuffle. A right rotation is the mirror image. The left child rises, the old root moves right, and the middle subtree still sits between the two keys. Again, order is preserved while height improves. AVL trees, red-black trees, and other balanced trees use different rules. Some track height strictly. Some use colors and black height ideas. The beginner idea is shared: detect too much lean and repair it locally. When height stays small, the receipt stays small. Search pays for the nodes on the path, not for every key in the tree. Balanced trees keep that path near logarithmic growth, so doubling the data adds only a small number of extra levels. Balanced trees do not rebalance for free. Insert and delete may need bookkeeping and rotations, like a repair crew tightening the structure after changes. The trade-off is worth it when you need ordered operations and reliable short paths. A hash table is excellent for exact lookup, but it does not naturally keep keys sorted. A balanced tree supports ordered traversal, ranges, predecessor, successor, and nearest direction questions. Because of the order rule, walking left subtree, then node, then right subtree visits keys in sorted order. That is something heaps and hash tables do not give you for free. For a range query, picture a spotlight on the middle shelves. The tree can skip branches that are entirely too small or too large, follow the boundary paths, and collect only the keys inside the interval. Balance keeps those boundary walks short. Database indexes often use tree-like structures because they need ordered access, ranges, and updates. The index is not just a pile of records, it is a maintained branching shortcut from a search key to the right neighborhood. A plain binary search tree can still degrade to linear time if it becomes tall. Balanced trees exist to protect against that shape failure. The speed promise belongs to the maintained balance, not to the word tree alone. Trace one search slowly. Looking for 40 starts at 50. 40 is smaller, so the right side of 50 is irrelevant. At 30, 40 is larger, so the left side of 30 is irrelevant. At 40, the search stops. The path is short because the shape is healthy. Now imagine inserting 10, 20, 30, 40, 50 in that order into a plain tree. Each value is larger than the last, so every step goes right. The order rule is still obeyed, but the shape is terrible. Correct structure can still make slow work. The reason rotation works is range logic. If 30 is less than 40 and 50 is greater than 40, rotating the local shape does not change those relationships. The middle subtree stays between its boundaries. That is why the tree can move without forgetting its order. Balanced tree families differ mainly in bookkeeping. AVL trees watch height more strictly. Red-black trees use color rules to limit bad shape. You do not need every case yet. The shared story is detect lean, repair locally, and keep paths short. The receipt for balanced trees is different from hash tables. Exact lookup is reliable and ordered. Range queries and sorted traversal are natural. Updates cost some maintenance. If your future questions care about order, that maintenance buys the right shortcut. For a range from 30 to 70, the tree can ignore branches that are entirely too small or too large. It walks boundary paths, collects keys inside the interval, and skips irrelevant subtrees. Balance keeps the boundary walks from becoming long corridors. Compare two shapes with the same keys. In the balanced tree, finding 40 may take 3 comparisons. In the fallen staircase, it may take 5 or 6. The values did not change. The code idea did not change. The shape changed the amount of work. Balance is not aesthetic symmetry. It is a performance promise. The tree is allowed to be a little uneven, but not so uneven that paths grow like a list. That is why balanced trees use rules and repairs after updates. When you hear balanced tree, picture two promises working together. The order promise says which direction to walk. The balance promise says the walk will not be too long. One promise without the other is not enough for reliable performance. Think of a balanced tree as a library shelf with branching signs. The signs give direction, but the building also needs good architecture. If every hallway becomes one long corridor, the signs stop saving time. Recap: the order rule makes search directional. Height is the cost. Bad insertion order can make a tree fall over. Rotations preserve order while repairing shape. Balanced trees keep ordered operations reliably short. Next, we will move from ordered trees to graphs. Once data is connected by relationships, the question changes from where is this key to how do I move through this network without getting lost.